Welcome to the second video of first lecture of week 1 of the course. In this course, we have started with vectors. So, now in this lecture, I will review the basics of vectors. To specify certain physical quantities, we require numbers. For example, the price of a pencil is rupees 5, just we require number only. Similarly, the weight of the apples in a box is, suppose it is a 3 kg. Okay. So, here also we need only numbers, whereas to specify certain physical quantities, we require numbers and some more information like direction. For example, by taking the capital city of Madhya Pradesh, Bhopal as the origin, I want to specify the location of the Guwahati city. So, the location of the Guwahati city is approximately 1700 kilometer from the Bhopal city and in the northeast direction. So, here we need number as well as the direction to state the position or location of the Guwahati city. So, with these required information to specify the physical quantities, they are broadly classified as scalars and vectors. First of all, we will see the definition of vectors. A vector is a physical quantity which has both magnitude and direction. For example, in a projectile of a particle, position of the particle or displacement or velocity or acceleration are vector quantities. Similarly, force, electric current, electric field are also vector quantities. In R2 or R3, vectors can be represented geometrically by a line with the arrow at the end. The direction of the arrow specifies the direction of the vector, and the length of the arrow describes the magnitude of the vector. The tail of the arrow is called the initial point of the vector and the tip of the arrow is called the terminal point. Next, we define a concept called magnitude. So, this is something like modulus, absolute value, similar thing to generalizing to the vector. Let capital A is equal to A1, A2, An be a vector in Rn. Then the magnitude of a vector, the vector A is denoted by modulus A or norm A. So, if you put the double vertical line, it is called norm, otherwise single vertical line normally usually called as modulus. Modulus A or norm A, and it is defined as square root of A1 square plus A2 square plus up to An square. For example, if I take A as the vector 1, minus 2, 3, then the magnitude of the vector modulus A is equal to square root of 1 square minus 2 square plus 3 square, that is square root of 1 plus 4 plus 9, which is square root of 14. Okay. Next, I am taking a vector in the 5-dimensional space. B is equal to 0, 0, 4, 0, 3. Then modulus B is square root of 0 square plus 0 square plus 4 square plus 0 square plus 3 square, which is basically giving us square root of 25, which is equal to 5. So, in Rn, this magnitude of the vector is the Euclidean distance between the origin and the point capital A. So, next we will move to the defining the concept of scalars. A scalar is a physical quantity which has magnitude only. As I said, the price of the pencil is rupees 5, only I need a magnitude only, number only. Okay. So, in physics, some examples like mass, temperature. So, temperature of Guwahati city is 30 degrees Celsius. Okay. So, the distance between Bhopal and Guwahati is 1700 kilometer. Okay. Speed, energy, electric charge, all of them are scalar quantities. On vectors, we will introduce now algebraic operation, namely addition operation. So, it is also called vector addition. Let capital A equal to A1, A2, An and capital B is equal to B1, B2, Bn, be 2 points or vectors in Rn. Then the addition, that is A plus B, is defined as coordinate wise addition. Okay. This add A1 with B1, that is A1 plus B1. Then second coordinate is A2 added with B2. Then nth component is An added with Bn. Okay. This is coordinate wise addition. A plus B equal to A1 plus B1 as a first component, A2 plus B2 as a second component and An plus Bn as the nth component. For example, if I take A equal to 1 minus 8 and B equal to minus 2 comma 5, these are the two vectors in R2, then A plus B, first I add with 1 with minus 2, okay, that is the first component, then minus 8 added with 5, that is the second component. So, the answer is minus 1 comma minus 3. A plus B equal to minus 1 comma minus 3. Similarly, I am taking another example, a vector in R4, that is capital A equal to 1, 1, 1 minus 1 and capital B is minus 2 comma 1 minus 5, 3. These are the two vectors in R4. Then capital A plus B, that is capital A plus capital B. The thing. So, normally I call capital letter to denote the vectors. So, I may say just A also simply instead of telling capital A always. So, A plus B is equal to the coordinate wise addition 1 plus minus 2, that is the first component giving minus 1, 1 plus 1, that is the second component gives 2, 1 plus minus 5 gives the third component minus 4 and minus 1 plus 3 gives the fourth component 2. Okay. Now, let us see the properties of this addition operation. The first property is A and B in Rn, then A plus B is also in Rn. Okay. So, adding two vector in Rn gives another vector in Rn only. It is called closure property. Next property is associative property. A plus B, first you add A plus B, then add with C. This is equal to first adding B plus C and then adding with A, okay, for all A, B, C in Rn. So, this is associative property. So, the order in which we are adding these three vectors does not matter because they are going to yield the same value. Next property is existence of additive identity. There exists a element 0, 0, 0 is origin, okay, in Rn. So, this is denoted by a bold face letter 0 or 0 with arrow symbol. So, it is 0 vector such that A plus 0 equal to A for every A in Rn. So, this is the existence of additive identity, because why it is called additive identity, because this is identity element with respect to this addition operation on the vectors. Next property is existence of additive inverse. For each element or each vector capital A in Rn, there exists an element, okay, if A is A1, A2, An, then the element, another element minus A1 minus A2 minus An, which is also in Rn and denoted by minus A, and call inverse element such that A plus minus A equal to 0, that identity element. So, this is the fourth property of vector addition. Then the next property is commutative property, that is A plus B equal to B plus A for all A and B in Rn. So, basically In abstract algebra, a set, non-empty set with a binary operation satisfying these first four properties is called a group. Okay. If a group satisfies the additional property of commutative, then it is called abelian group. So, in that abstract algebra concept wise, this Rn with respect to addition operation forms an abelian group, we can say like that. Okay. Next, we will introduce another operation involving a scalar and vector. Okay. So, which is called scalar multiplication. Okay. Let capital A and capital B be two vectors in Rn. Let lambda be a real number. We call lambda as a scalar and we take this scalar from real field. It is called field, means it is basically a concept in abstract algebra. Okay. Otherwise, just take it as a set of all real numbers. In advanced level course, one can take these scalars also from complex number, that is set of all complex numbers, or complex field also one can take it. But in this course, we assume that the scalars are coming from the set of all real numbers, that is real field. Okay. So, the scalar multiplication operation is defined, basically how it is defined. This is a product operation between a scalar and a vector, and it is called as a scalar multiplication and is defined as lambda A is equal to lambda A1 as a first component, lambda A2 as a second component, lambda An as the nth component. That is, each component we are multiplying by this scalar lambda. If A belongs to Rn, lambda belongs to R, then the resultant lambda A is also a vector in Rn. For example, I take lambda equal to 3 and capital A as the vector in R4 as 1, 8, minus 2, minus 9, then lambda times A, basically I have to multiply component wise. 3 into 1 is the first component 3, 3 into 8 is the second component which is 24, 3 into minus 2 is the third component which is minus 6, 3 into minus 9 as the fourth component which is minus 27. So, the lambda times A, that is 3 times A is this vector 3, 24, minus 6, minus 27. Next, we will see the properties of the scalar multiplications associated with vector addition. So, take capital A and capital B is the vectors in Rn, lambda is a scalar coming from set of all real numbers. Then lambda, the product of lambda with A plus B is equal to product of lambda with A scalar multiplication lambda A plus scalar multiplication lambda B for all AB in Rn and lambda in R. Next property is the scalars lambda 1 plus lambda 2, this scalar multiplication with A is equal to scalar multiplication lambda 1 with A plus scalar multiplication lambda 2 with capital A for all the vector A in Rn and for all scalars lambda 1 and lambda 2. Third property is the scalar multiplication of lambda 1 with the vector lambda 2A is equal to the scalar multiplication of lambda 1 lambda 2 with the vector A for all capital A in Rn and for all scalars lambda 1 and lambda 2. The last property, the 1, the real number, this 1 belongs to R. Okay. So, this scalar times A, the scalar multiplication 1 with A is equal to A for all A in Rn and here 1 belongs to R. Okay. So, next we want to define a multiplication operation between vectors, okay, a product operation. The first one we are going to define as called dot product. Let capital A is equal to A1, A2, An and capital B equal to B1, B2, Bn, B2 vectors in Rn. Then the dot product between these two vectors A and B is denoted by A dot B, or simply AB also we denote it, and is defined by A dot B is equal to A1 B1 plus A2 B2 plus AN Bn. That is, coordinate wise you multiply and sum it. A1 B1 plus A2 B2 plus and so on AN Bn. So, coordinate wise multiplication we are doing here. So, this product is called dot product. Okay. So, we will see some example. It is also called inner product of A and B and is denoted by this symbol. Okay. This less than A comma B greater than. Okay. So, this way also it is denoted, and it is also called inner product of the vectors A and B. The first property about this dot product is it is commutative, that is A dot B equal to B dot A. So, either you can do the dot product in any order, whether A with A dot B or in B dot A, because they are going to give same value. Another observation about this dot product gives the value which is a scalar. Okay. So, this is operation between two vectors yielding a scalar value. Examples. First example, I take two vectors in R3. Capital A is equal to 2, 8, minus 2. Capital B is 1, 2, 1. Then A dot B, first I am doing coordinate wise multiplication 2 into 1. Then second coordinate 8 into 2. Then third coordinate minus 2, 1, and they are summed it. Okay. So, which gives 16. Next, I am taking two vectors in R4. The first vector capital A is equal to 1, 8, minus 2, minus 9. Capital B is 1, minus of 3, 1 by 3. Then A dot B, just to coordinate wise you multiply and sum it, add it. So, that gives minus 12. Okay. So, this dot product, inner product gives way to define angle between two vectors. Let capital A equal to A1, A2, AN and capital B equal to B1, B2, Bn be two non-zero vectors in Rn. Let theta be the angle between this A and B. Suppose in R2 thing I have two vectors. Okay. This is A. So, this is B. So, this is the angle theta. Okay. So, this angle theta satisfies that cos theta equal to the dot product of AB divided by modulus A into modulus B. Okay. Cos theta equal to the dot product of AB divided by magnitude of A and magnitude of B, okay, or modulus we can say. Two non-zero vectors A and B in Rn said to be orthogonal if this dot product A and B is equal to 0, because the angle between these two vectors is 90 degree, cos 90 degree equal to 0. So, that angle between two vectors is 90 degree, then we call it they are orthogonal. So, two non-zero vectors A and B in Rn is said to be orthogonal if and only if the dot product or the inner product between A and B is equal to 0. So, I will give one example. In two vectors in R3, I want to find the angle between these two vectors. The vector A is 0, 1, 0, the vector B is 0, 1, 1. Okay. So, the dot product between these two vectors is basically giving us 1, modulus A or magnitude A is 1, modulus B or magnitude of B is root 2. So, cos theta equal to dot product of AB divided by modulus A and modulus B, the product. So, which is equal to 1 by root 2. Cos theta equal to 1 by root 2 means theta equal to 45 degree pi by 4 degree. Okay. So, you can easily visualize these two vectors, drawing these two vectors, and you can see that the angle between them is a 45 degree. Now, Specifically in R3, we want to define some more concepts, another kind of product which is called cross product or vector product. Another two things are scalar triple product, vector triple product, which is involving with the three vectors things. Okay. So, the first we will introduce what is cross product or vector product in R3. Let capital A equal to A1, A2, A3 and capital B equal to B1, B2, B3 be two vectors in R3. Let theta be the angle between A and B. The cross product or vector product is a vector quantity. So, this is a vector quantity written as A cross B, whose magnitude is modulus A modulus B sin theta and whose direction is perpendicular to both A and B in a right handed sense. So, this A cross B is equal to modulus A modulus B sin theta u vector, where u vector is unit vector perpendicular to both A and B in right handed sense. So, here the vector A is there, vector B, the angle between them is theta. So, the A cross B is perpendicular to both A and B. Okay. So, cross product A cross B is a vector quantity which is perpendicular to both A and B in right handed sense, and their magnitude is modulus A modulus B and sin theta. So, this can be defined in another way, or this can be proved this as a property. Let capital A equal to A1, A2, A3 and capital B equal to B1, B2, B3. Okay. You can write it in vector notation which is familiar in the school mathematics, like A1i, A2j plus A3k. Here I, j, k are the unit vectors along the x axis, y axis, z axis direction. Similarly, B can be written as B1i, B2j, B3k. Otherwise, you can write it as a point. Okay. So, both the way we can write it. Then A cross B is defined as 3 by 3 matrix determinant. The matrix determinant first row is ijk vectors. The second row is the basically the first vector A, that is A1, A2, 3, their components A1, A2, A3. Third row is the components of the B vector B1, B2, B3. Okay. So, the value of this determinant is basically a vector quantity. Okay. For example, you take A equal to 1, 3, 0, B equal to 2, 1, minus 1, then A cross B become the 3 by 3 determinant. The first row is the vector, unit vector I, j, k along the coordinate axis. The second row is the vector A components 1, 3, 0. Third row is the components of the B vector 2, 1, minus 1. Then this determinant is equal to minus 3i plus j minus 5k. Now, we will see the properties of this cross product. The main important property of this cross product is it is not commutative. Okay. That is, A cross B is not equal to B cross A. Actually, A cross B is equal to minus of B cross A. Two vectors A and B are parallel, then what will happen? This A cross B, the two rows are become basically one is the scalar multiple of another row. So, and hence the determinant becomes 0. So, that thing yields that two vectors A and B are parallel if and only if the cross product, that is A cross B, is equal to 0 vector. If and only if they are scalar multiples of one another. Next property is if you do cross product A with itself, then it becomes 0 vector, because two rows are identical in that determinant and hence the determinant value is 0. The magnitude of A cross B is the area of parallelogram made by two vectors A and B. Okay. So, basically, so these are the two vectors A and B. Okay. Then you make the parallelogram with the same thing. So, the area of this parallelogram, this is also A vector. Okay. So, this is also mod. Okay. The magnitude of A cross B is the area of this parallelogram made by these two vectors A and B as a adjacent edges. The area of the triangle made by these two vectors, okay, that is half of that parallelogram area, that is basically modulus of A cross B or magnitude of A cross B divided by 2. The cross product is distributive over addition, that is, the cross product of A with B plus C is equal to the cross product of A and B plus the cross product of A and C. Okay. Similarly, the cross product of the vector A plus B with C is equal to the cross product of A and C plus the cross product of B and C. If lambda is a scalar, lambda is a, take the scalar lambda, then scalar multiplication lambda times A cross B is equal to lambda A, this vector cross product with B, or that is equal to A cross product with lambda times B vector. So, next we want to define another concept, which is scalar triple product. Let this concept is defined for between three vectors. Let capital A, capital B, capital C be three vectors in R3. Then the scalar triple product of A, B and C is denoted by A dot B cross C, or it is denoted by with the square parenthesis, put it, and A, B, C inside the square parenthesis, and it is defined by a determinant of a 3 by 3 matrix. First row as the components of the A vector, second row is the components of the B vector, third row is the components of C vector. Okay. So, a determinant of a matrix is a scalar quantity. So, this scalar triple product is a scalar quantity, and we can see this example. I take the vector capital A as 2, minus 3, 1. The vector B is taken as 2, 0, minus 1. The vector C is taken as 1, 4, 5. Then the scalar triple product of A, B and C is basically 3 by 3 matrix determinant, whose first row is the vector A components, whose second row is the components of the vector B, whose third row is the components of the vector C. Then put it like that, and then define the determinant value, which is equal to 49. The scalar triple product is a scalar quantity. Okay. So, the properties of this scalar triple product is the dot product of A with the vector B cross C is equal to the dot product of A cross B vector with C. The vectors A, B and C can be permuted cyclically, that is A dot B cross C is equal to B dot C cross A, which is equal to C dot A cross B. If any two of the vectors A, B and C are equal, then its scalar triple product becomes 0. If all three vectors A, B and C lie in a plane, all of them are lying in the same plane, then its scalar product is 0. The volume of the parallel pipe that has vectors A, B and C as adjacent edges is magnitude of this scalar triple product, that is A dot B cross C. The volume of the tetrahedron made by these vectors A, B, C as adjacent sides is equal to the magnitude of the scalar triple product A dot B cross C divided by 6. Next, we move to another concept, vector triple product. Here also this concept also between three vectors in R3. let capital A, capital B and capital C be three vectors in R3, then the vector triple product of A, B and C is defined by A cross B cross C. So, first find the cross product of B and C and then do the cross product of A with B cross C. It is a vector quantity first of all. The brackets in these expressions are important because A cross product with B cross C is not equal to A cross B product with C. For example, I take the vector A, B, C like this, A equal to 1, 2, 1, B is 0, 1, 1 and C is 2, 1, 0. Then first I have to compute B cross C which is minus 1, 2, minus 2. Then cross product of A with B cross C. So, that is computed here and which gives the minus 6, 1, 4. The properties of vector triple product is this A cross B cross C, that is cross product of A with the vector of B cross C is equal to A dot C, this is a scalar quantity, okay, with scalar multiplication with B minus A dot B become a scalar. So, that scalar with the multiplied with the vector, this is a scalar multiplication. Okay. So, A cross B cross C is equal to A dot C B minus A dot B C. A cross B cross C, that B cross C is first within the bracket, first operation, then is equal to the cross product of minus C with the vector A cross B. So, because of this, using this first property, I can get the third one. A cross B cross C equal to minus of C dot B with A, this scalar multiplication, that is C dot B is a scalar multiplied with this vector A, plus C dot A is a scalar which is multiplied with the vector B. So, A cross B cross C, this one is equal to minus C dot B scalar multiplied with the A plus C dot A scalar multiplied with B. This vector triple product become commutative provided B cross A, this cross product of B with A cross C is equal to 0. Only in this case, these two quantities are equal. That is, cross product of A with B cross C is equal to the cross product of A cross B with the vector C. So, next we introduce a small concept called projections on components or projection along coordinate axis or projection on a unit vector. Okay. Let E1 is basically first place component is 1, remaining all component is 0. E2 is the second component is 1, the remaining all other components are 0. En is the nth component is 1, all other components are 0. Be the unit vectors along the coordinate axis of Rn. Then the point capital A, A1, A2, An can be written in the vector form like this, A1, E1 plus A2, E2 plus An, En. The orthogonal projection of A on the vector Ek is denoted by this proj Ek of A projecting, and it is defined by dot product of the vector A with Ek vector. So, this become a scalar quantity. This scalar is multiplied with the vector Ek. Okay. So, that basically A with Ek you multiplied, only we will get so this A dot product of Ek gives Ak. So, that Ak multiplied with the Ek vector. So, the orthogonal projection of A on the vector Ek is a vector basically whose magnitude become the kth component of the vector A or multiplied with the unit vector on that kth coordinate axis. So, instead of this Ek, the unit vector along the coordinate axis, one can take the unit vector, any other unit vector also you can take it. Suppose u is a unit vector, then the orthogonal projection of the vector A on the unit vector u is defined by dot product of A with u and multiplied with the scalar multiplication with the u vector. Okay. then the vector B, which is A minus projection of A on U, will be orthogonal to the vector U, and we call this is the vector component of A orthogonal to U. So far we have done the basics concepts of vectors as a review. Then we will move to the Rn, space Rn, and how we are going to do further in this direction is basically we have algebraic operations on vectors. Okay, algebraic operations of vectors, they namely vector addition, scalar multiplication. These operations we have seen in this lecture. This can be generalized to the concept of vector space in linear algebra. Okay, so these concepts are basically generalized as the vector spaces. Okay. Next thing is the absolute value or modulus of a vector we have seen, or a mob thing. Okay. So that concept is basically a distance from the origin to that point or thing. So instead of distance between origin to that point, the distance between 2 points, we can have that concept. It can be generalized like that. Okay. The absolute value modulus can be generalized as a to the concept of distance between 2 points or distance between 2 elements. That distance is called metric. Okay. So this concept is basically generalized as a metric space, which is used to study the convergence of sequences. Also it is used to study limits of functions, continuity of your functions, etc. Next we have seen dot product, inner product. So that with the help of that we have defined the angle between two vectors. Okay, the angle between two vectors become 90 degree, we call that is orthogonal. So that orthogonal concept is basically leads the concept of orthogonality in general setup. Okay. Now algebraic operation is one side, distance concept is another side. Now we want to combine these two things. Okay. Algebraic operations on vectors plus the distance concept. So such setup is basically we call it as norm. Okay. So that is a normed vector spaces. So normed vector space in which there is a distance which is called norm. That is also algebraic operation. This vector addition, scalar multiplication also available. Okay. So vector space, or it is also called linear spaces. So normed vector space, normed linear space. So basically this dot product also yields some kind of distance. Okay. I can do the inner product of dot product of A with A itself, that is basically gives the modulus A square. Okay. So this dot product or inner product also gives some kind of not only angle, it gives one kind of distance, a specific distance also it gives. So the algebraic operations on our vectors plus angle between two vectors, that concept basically gives us the inner product, and that inner product is basically leads to the concept of inner product spaces. Okay. So these concepts are basically coming from linear algebra. Okay. And then the linear algebra and analysis concepts are combined together as finally the subject called as a functional analysis. Okay. Mainly study about all these properties. We now end this video with this information, and we will meet you in the next video. Thank you.